In the early years of the 20th century, several experiments gave us clues about the structure and the mechanics of the atom. In this presentation, I will discuss a groundbreaking experiment performed by Ernst Rutherford that revealed the basic structure of the atom. In the 19th century, the atom was believed to be a tight cluster of positive and negative charges. Rutherford's experiment revealed that the atom was actually not densely packed, but contained mostly empty space. He claimed that all the positive charge in the atom must be at the center, and that this positive center was surrounded by electrons. He learned about the structure of the atom with his famous alpha particle scattering experiment. Rutherford shot tiny alpha particles at a thin gold foil and used the deflection angles to learn about the structure of the atom. An alpha particle is made up of 2 protons and 2 neutrons. It's simply a helium nucleus. This is a simulation of Rutherford's experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
An alpha particle is so tiny that it cannot be seen with even the most powerful microscope. It has a charge of +2 and is made up of 2 protons and 2 neutrons. Most of the alpha particles went straight through the thin gold foil, but some were deflected a wide variety of angles. What surprised Rutherford most was that some of the positively charged alpha particles were deflected at extremely wide angles. Some even were deflected straight back at an angle of 180 degrees. Rutherford concluded that these large deflection angles could only be possible if something in the atom were extremely positive. He theorized that all the positive charge must be concentrated in the center of the atom. We now call that part of the atom the nucleus. He explained that the size of the scattering angle was related to how close the alpha particle was to the nucleus. If the alpha particle was deflected at 180 degrees, it was because it had a very rare head-on collision with the positively charged nucleus. The scattering of the alpha particle was due to a repulsive electrical force between the positively charged alpha particle and the positively charged nucleus. This force is also called the Coulomb force. Rutherford wrote that he was shocked at the large scattering angles. Only a very strong positively charged object could cause the alpha particle to deflect at these huge angles. Rutherford concluded that the only explanation for the fact that most of the alpha particles passed straight through the gold foil was because most of the volume of the atom was made of empty space. The nucleus makes up only a tiny fraction of the volume of the atom.
This is Cambridge University in England, where Ernest Rutherford, Niels Bohr, and other famous physicists did scientific research. Imagine a single atom the size of this courtyard.
If we think of that being the size of an atom, then the size of the nucleus would only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
There are objects in space that illustrate how much empty space there is in the atoms that make up our world. A neutron star is created when a massive star runs out of fuel and collapses. This tremendous gravitational collapse squeezes all of the empty space out of the atom. Electrons merge with protons and create neutrons. The density of this neutron star is so enormous that a teaspoon of a neutron star would weigh 20 billion pounds. To give you an idea how small the nucleus is compared to the total volume of the atom, if an atom were the size of a football stadium, the nucleus would be the size of a marble. Because the alpha particle is so tiny and the atom is made up of mostly empty space, it is very easy for it to pass through the atom without being deflected by an electrical field. Even though the nucleus makes up a tiny portion of the atom's volume, it contains virtually all the mass of the atom. Rutherford proposed that all of the atom's positive charge was located at the center of the atom, or the nucleus. So if atoms are made of mostly empty space, and everything we know is made up of atoms, why is matter so solid?
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. But what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields.
When the electrons come within a very small distance of each other, they begin to repel each other, and that's why things appear to be solid when they are actually not. Now, you may think that I'm sitting on this chair, but actually that's not true. I'm actually hovering over this chair 10 to the minus 8 centimeters over this chair, because of the electrons of my body are repelling the electrons of this chair.
I don't know if you noticed it, but in our discussion about the structure of the atom, we never mentioned the neutron. This is because the neutron was discovered 20 years after this experiment by a British scientist named James Chadwick. This is the end of my presentation on the Rutherford model of the atom.